everyone. This time we'll bring together almost everything we've learned about electromagnetism or electric and magnetic fields. We'll start this topic of electromagnetic waves by thinking about constant current in a conductor. Here we have a bunch of equations that are in fact called the Maxwell's equations. They will exhaustively explain every known phenomenon of electric and magnetic fields. And if you look at the last one, it says that if we have a constant current, a constant magnetic field is produced. And we know that already, that the loop or the magnetic field around a constant current loop looks something like this. Dives into the page on the right hand side and comes out on the other one. Now, what happens if the current wouldn't be constant, but it would be changing as a function of time? That is, the magnitude of it changes or even the direction. In that case, we have a changing current, which means that we have a changing magnetic field. The third equation from the top, this is the Faraday's law, which we already talked about, and it says that if we have a changing magnetic field, we have changing magnetic flux, and that produces an electric field. So somewhere here, when we have a changing magnetic field, electric field should also be created. If the current is changing, the magnetic field is changing. Magnetic field is changing again here, and because it's changing in direction and magnitude, it means that also the created electric field is changing. So we have some kind of electric field happening not in the conductor, but outside the conductor in the free space or air. So, as discussed, these electric fields, they in fact form loops like this. In fact, they can be also seen here on this last equation, which says that if we have a changing electric field, that will generate a magnetic field. And again, changing magnetic field creates a changing electric field, and that in turn again produces a magnetic field. So suddenly we are in this dance between electric and magnetic fields, that this process keeps repeating, and in fact these fields will travel in time and space in some manner. And what we are seeing here are in fact electromagnetic waves. Some of the energy from these charges moving in this conductor are being radiated outwards. You might have wondered, what is this extra term that allows this interchange of electric and magnetic fields? Because we haven't talked about this one before. So in fact, this is telling that magnetic field is not only generated by a current in a conductor, but it can also be produced in empty space if there is a changing electric field. And this was the discovery of Maxwell that completed the picture of electromagnetism, and that's why these equations are called the Maxwell's equations. In essence, they predicted this behavior that we described, that is, that electromagnetic waves can propagate in empty space no need for any kind of medium. And that is the backbone of our modern society with all our communication systems. So the repercussions of this discovery are of paramount importance to all of us. Before we move on to the electromagnetic waves themselves, I'd like to recap what we learned so far in terms of charges. So first, when we have just electric charges, what we observe is an electric field. In case of a point charge, for example, we have this radial field that diminishes as a function of distance, but it's purely an electric field. Then if we make these charges move, so when we have moving electric charges, like in this conductor, we also create a magnetic field. Third, if these charges are not moving, but they are accelerating, that produces the described changing magnetic fields, and which in turn gives rise to changing electric fields. And in fact, electromagnetic waves, which are a combination of changing magnetic and electric fields. When electromagnetic waves are produced for communication purposes, the charges in a conductor or antenna are usually accelerated by a sinusoidally varying voltage source, which gives rise to sinusoidally varying electromagnetic waves. If you could see the varying electric and magnetic fields, they would look something like this. So the electric and magnetic fields are perpendicular to each other, and they are also perpendicular to the direction of the wave where it's traveling, or the direction of motion of the wave. Like any wave motion or sinusoidally varying wave, we can define a wavelength, lambda, and also a frequency at which these waves are oscillating. And they have a certain velocity, of course, and that is the speed of light in whatever medium they are propagating in. So the speed of light equals the wavelength of the electromagnetic wave times the frequency of the wave. And in fact, Maxwell himself, from these equations, after realizing this important missing part, he was able to theoretically predict the speed of light to be about 3 times 10 to the 8 kilometers or meters per second. And this is the speed of light in the vacuum, and it's not very much different from the speed of light in the air. In this figure you can see the electromagnetic spectrum, or spectrum of all electromagnetic waves or electromagnetic radiation. So the most common thing that comes usually to mind when we're talking about electromagnetic waves are the radio waves that we use for long distance communication, for example radio or TV. But also microwaves in a radar or in a microwave oven, they are electromagnetic waves, but their wavelength is shorter. The wavelength decreases in this direction, which in fact means that the radiation becomes more energetic, or in the other way around it, there's more energy bound to those E and M fields as they propagate. After microwaves, we have infrared radiation, which is generally the heat we feel from the sun, for example. We absorb the infrared radiation, and our skin is sensitive to that. And after that, the very important visible light region for our vision. Then we have even shorter wavelengths of ultraviolets, X-rays, and gamma rays. And after that, the naming convention stops, but there is no ultimate limit how small the wavelength can be. When we are categorizing all these different kind of waves according to the wavelength, we are making the assumption that they are sinusoidal. Then you might ask, why is it that all the electromagnetic waves in nature are sinusoids? And the answer is that necessarily they are not. It is just a mathematical fact that any kind of shape of wave, for example a sawtooth wave like this or a square wave like this, can be expressed as a sum of different frequency sinusoidal waves. For example, something like this, we have this fundamental frequency and then a frequency something like this, or in the case of square wave, fundamental mode, and then we have these high frequencies that give the sharp transitions. So in reality, no one really knows if electromagnetic waves are in fact sinusoids. It just happens so that our mathematics describes the behavior of electromagnetic waves very well if we assume them to be sinusoidal. And usually we use sinusoidals as well because solving the Maxwell's equations are the easiest way, or easy to do when using sinusoids. But as you will learn later on, electromagnetic waves, light for example, sometimes they behave like they were light, like they deflect and refract and interfere like any wave motion, and sometimes they behave as they would be particles. So no one really knows what is the fundamental nature of electromagnetic radiation, but according to our knowledge, the sinusoids will describe their behavior well enough, so there hasn't been any reason for not to use that kind of mathematics to describe them.